Hi, guys. So I know a fair amount of you, and you may be surprised, like, why is Tracy Bannon talking about machine learning, AI, ML? We think of her as kind of doing the operationalizing of architecture. How do you actually take something out to production and get it there? And the backstory on that is that I've been working with Ryan for about 2 years now in our cloud practice. So within Deloitte, I'm a chief engineer, and I'm focused on cloud native. And throughout that journey, getting to know the different CSPs and getting to know what my clients need has gone from lift and shift and refactor to this massive run towards analytic in many, many different forms. My role in that has been to provide data ops, helping to make sure that all of these incredible models that Ryan's going to walk through can actually go from the data scientist out to the mission owner so that they can get what they need. Been with Deloitte for about, 13 years, and as I said, I focus in the cloud space. Ryan and I have been working together for 2 years on the Google side of the house, so you'll see a little bit of a Google emphasis in the things that we're going to talk about today. Ryan, do you want to introduce yourself a little bit more?
Sure, yep. I've been with Deloitte for about the last 6.5 years. Some of you might have remembered me last year. I was here to talk about blockchain, smart cities, and many of the other things that appears on your innovation bingo card. But I'm just fascinated by all technologies and was already looking into machine learning at the time. And there's been a couple of products that have been released just within the last year or so that makes it to where I'm confident anyone in this room will be able to start building machine learning models immediately.
So, okay, here's the agenda. We'll just skip right past this and get to some interesting stuff. And I'll stand back here. I can flip through these for you. This is the public service announcement. I can't get this out of our risk analysis unless I have something up there that says we work for Deloitte, and that's great. Why does it matter to anybody at all? Just that Ryan and I have access to a lot of different types of projects in a lot of different places so that we can actually kind of watch trends in different markets. I go across commercial and government. Ryan's primarily in government right now, but we're seeing a lot, especially in the federal space. It's pretty incredible what we're seeing. On the civilian side with the uptick in machine learning. Now, you'd think that defense would want to have a lot in machine learning analytics space. They do. But it's a lot more difficult for them to adopt any of the cloud technologies right out of the bag because of all of the different types of controls, DISA regulations that are in place before you can get something out to the cloud. If you were to release a new service today into commercial cloud, it could take up to 3 years for the Department of Defense, Navy, Army, et cetera, to be allowed to use it after it went through all of the security checks and balances and permissions. So why does that matter? It just means that we have some visibility, like I said. Let's go ahead and take a look at this. So, this is a holy war when it comes to what is artificial intelligence, what's machine learning, what's analytic. Everybody is going to disagree with this, and that's okay. All we wanted to show is that there's this continuum, right, that started with ain't got nothing. Some people would say that down there in that no analytics are the really super trendy process robotics. Mental note, hate the term process robotics. It's scripting on steroids, but I get it. How can I do something predictably and gather some information from it and look backwards at it? Going across the scale, right, we went from reporting to BI to generalized analytics. Machine learning to me is where I can build a repeatability and I can allow that algorithm to grow smarter with the parameters that we've put there, but I could still repeat it with a human. Machine learning, in my mind, with machine learning algorithms, at the end of the day, I could still do it with a human. When I get over into artificial intelligence is where, oh, hi, Andrew Chu. When I get over into artificial intelligence is where there's a wow factor, a pizzazz factor, or Ryan likes to say inspiration that happens. There is a CMU professor, and I wrote his name down. Let me look at this really quick. Andrew Moore. I was looking for something that I could explain to my mom or dad what AI is. And the quote was something along the line that when science and engineering are at the point of helping computers to do the things that up until this moment we thought only humans could do. So there's a good or should I say, good example for this. Are you guys familiar with DeepMind, Google's DeepMind? And I think it's AlphaZero, AlphaGo,
Yeah,
AlphaZero.
yeah.
AlphaGo is, we had the Big Blue and we played chess in the 70s and the 80s. There's a Chinese game called Go, and in order to, and you might tell this story a little bit better than me, but there came a point where there was a challenge between human to machine, and the choices that the AI made throughout this, there was a 1 in 10,000 chance that a human would ever make that kind of a decision. So it was an inspiration moment, it was a pivot point. And since that time, those algorithms and that continuing training of itself and educating of itself and making more decisions of itself has made it so powerful that there has been no one that has been able to defeat it, and it now plays itself. So when I think about AI, I'm thinking about that wow pizzazz factor when a machine can actually do something or come up with a decision point that I might not have been able to get to. Sometimes people get a little scared about that, sometimes not. All right, so we'll cover this stuff just because it tells you that it's big and it's important. There's a lot going on in this space. That's all that this is about. And why this matters to me as somebody who's on the operationalizing part of it is that I need to figure out how to take all of these things. And the prior session to this, I got to hear a part of it, had some great information about data ops. How do I take those, all of the rigor that I apply to software engineering and apply it to models? Because people don't do that right now. I can tell you firsthand that as we have people, Ryan will tell you firsthand, as we have teams that are creating models, they're sloppy about what they're doing. They're not thinking about the quality of the models. They're not thinking about testing a model. No, you don't. Why would you test a model? Look, I got this really great answer. This is obviously a model that works, therefore it needs to go to production. No. Your model needs to be tested and validated, and I need to see that it's consistently learning and getting better, right, as we go. Let's go ahead. All right, anybody here have the name data scientist after their name and on their email or their card or anything else? All right, so if you do, you probably have 15 or 20 job offers a day right now, right? Seriously, I'm really serious. I'm very serious about this. All of the analytic, all of the move towards machine learning, all of the need for AI is driving this huge boom in that we need people, but we don't have enough people. So that's just so we have some backdrop to talk about. Now we're at the point where if you have a doctorate, you can get out, you can get a job immediately. Now we're saying, well, now not just a doctorate, I can have my master's degree and some years experience. How can I take that and how can I make it so that I can leverage those people, but I can also make it so that Tracy Bannon can help to make a model, or Ryan Luckay can dispatch a team of 10 to come up with 10 models? Well, the CSPs are starting to do that, the cloud service providers. Let's go ahead. So what they're doing is they're developing tools, and we're going to show you, I think we have 3 or 4 different demos that we're going to show you across different types. Where before, the machine learning researcher was using TensorFlow. Our data scientist had some tools that they could use, but they aren't necessarily easy to use. This AutoML product on the right-hand side here, I can tell you that we can pull down a picture of 50 images, just use Getty, pull them down from the internet, train a model, and within an hour, less than an hour, we have a model that is repeatable and testable. So that's the whole idea of this democratization. It isn't necessarily making it, it isn't a decision that a firm is making. It means that the tools that allow people to make mission-critical decisions based on data, based on these algorithms, is becoming available to anybody. Let's go ahead. All right, you guys know this stuff. I think we'll skip right over this. Anomaly detection, neural networks, and prediction. The reason I'm saying is that we have examples of each one of these. So what I'm going to do, I'm super excited to start in, and we'll talk about anomaly detection. Ryan, do you want to go ahead and take over, and let's get into the demos?
Absolutely. So there's actually been a good number of presentations over some of the underlying technologies already. So I won't belabor the point, but I'll just talk through a couple of things in order to refamiliarize and contextualize. So as you know, we actually have some pretty advanced models for visualization and object detection and certain things as well, right? Me as a human know the difference between that table and that coffee cup. But when the machine looks at an image, all it sees is a series of pixels until we contextualize further. So being able to answer the simple question, is there a pothole on this road, without previous training, there's no way to actually be able to do that. So what we do mathematically is we effectively create a classification model, right? We have a set of parameters that say this is what an image of a road without a pothole looks like, and this is an image of one that does, right? And then if we want to start looking at things like anomaly detection, we have a series of predefined classifications, and then anything that either fits a predefined classification for something that we're looking for, or something that does not fit within any of the predefined classifications. That's more or less what we're talking about mathematically when we're talking about anomaly detection.
Hey, Ryan, it's really, part of it is almost a yes or no, a gladiator. Does it fit my preconceived my preconceived notions? Again, think about a child who's sorting things for the first time and putting it into a box. Your first machine learning algorithm is going to be probably that simple. Is that a beach ball? Is that a beach ball? Is that a beach ball? That's not a beach ball. Oh, wait, that's a face. Why is that not a beach ball? Oh, it was my chubby aunt. Right, so it's going through those motions, and it's providing the parameters to be able to do that classification.
Exactly. So based off of what I was saying earlier, well, humans are great at this, machines are not. Why are we having machines do this at all, you might ask? Well, it really comes down to a matter of volume, right? So being able to determine that that's a coffee cup and that's a table is great for that one-off example, but what if instead I'm looking at 10,000 or 10 million images? I'll be standing here a long time doing that, right? But it's something that machines are definitely better equipped to deal with volume, as we all are know pretty well. So when we're talking about credit card fraud detection, right? I don't know how many people in here have had a credit card fraudulent activity, right? Yeah, and how quickly do they catch those now versus how quickly they used to? Right, I almost instantly get that notification, and it's there with a pretty solid amount of accuracy, right? So that's what we're talking about. That's what these groups do. They're using these fraud analytics processes that we use, using classification models. So another example of this is, your spam filter, right? Wanted to provide one of my favorite examples, which is Gmail's spam filter, which has 99.99% accuracy regarding identifying something that's a spam email. That's personal because I've been using it for a long time and have been pretty impressed with how little spam I actually have to deal with in my Gmail versus some of my other email providers. All right, so let's get to some of the fun stuff, shall we? So we're going to talk about, now I have double amplification there. And
we're going to do all these demos live, but in the case that anything fails, we are prepared with video recordings of it. So if that happens, we've got it covered.
Okay, so what we have here is actually the default out-of-the-box user interface for these AutoML models. So as somebody who works better with GUIs, as I think many of us do, this is immediately a feature that I was drawn to. So all we have to do is upload the various data sets, and we get there. So let me click on potholes because this is one that I already trained. As you can see, there's 49 images of roads that do have potholes in it, and there's 47 of ones that don't. And I wanted to try to make sure I got a good spread, but all of these I found on the internet, right? So I didn't necessarily need to go buy any of these things. But also wanted to provide some context in terms of what I had to upload, right? So all I had to do was upload, let me see, potholes, right? A simple CSV that had where the image was stored and what that image was. So this was it, right? I just had to upload the images, and I had to upload this simple CSV to create my training model.
Well, you said what they were. This is a pothole. This is not a pothole. Mm-hmm. What you didn't have to do is you didn't have to digitize, which was something even 3 or 4 years ago, I would have to go in, and when I was working with a very simple model, we were digitizing the edges of lakes. because we were doing volumetric change detection. And so we needed to go around the edge to see where the water had receded. And it took a lot of effort, and we were paying people just to sit there and annotate where the edges of things were. This is able to detect that already.
Exactly. So then next up, all we have to do is click on Train New Model, which I don't have to because like any good cooking show, we already have the model built, and we're going to just talk through it. So Google just actually spits out a lot of pretty good stuff for just a CSV file. But what I want to focus on down here is the most important part, the confusion matrix, right? How, when it broke off a piece of that data set that I provided to it and then tested it against its own model, how frequently did it come to the right conclusion? So it was able to, with 100% accuracy from the test set that I gave it, predict whether a road had a pothole, and then 83% of the time determine whether or not it was a regular road. And I would love to be able to tell you why it came to some of those conclusions, but explainable AI is still one of those things that's just a little bit out of our reach, right? So the model's only as good as its predictive capabilities though, right? So let's go ahead and do that. I'm gonna give it an image that it's literally never seen before, and we will see whether or not it works. So let's go ahead and see whether it determines if there's a pothole in this image. It said with 100% confidence that there was a pothole here. And then all I would have to do is I can either use my REST API, which is just right here, or if I just want to have it in Python, they've conveniently provided that as well. We cannot embed the algorithm because it turns out Google does not feel like giving away its IP. So you do have that. You still have to be able to make the calls. But to provide some context, I made this model in 1 hour and 5 minutes. And over 30 minutes of that time was just trying to find the right images that I wanted to. So over the course of this session, you could have created a model for a visual classification.
Actually, that's your homework, is to go home tonight and make sure that you make a model.
All right, so predictive analytics.
Before we go on to that,
Yeah.
so just a couple of business cases that we're working on where we're using this anomaly detection that we just showed you. And we'll have some more examples of it in a couple of minutes. But that yes-no, the philosophical yes-no, we're using that with childcare. We're using that along with facial recognition. Is this that person? Is this not that person? We're seeing that with Customs and Border Patrol. So there are a number of different places where we're using anomaly detection. And Ryan already spoke to the fact that there's a lot in the banking industry. And so you can imagine with Treasury and with a lot of our government agencies and the amount of fraud that they're worried about, we're also seeing anomaly detection really crop up there as well.
So thank you, Tracy. Even though predictive analytics can use several types of models, in this section I want to focus on regression analysis because that is the one that most closely ties to the next demo that I'll be providing to you all. So for those of you who are not exactly aware about how we use regressive analysis in machine learning, it's actually very simple to something that just about everybody in this room has probably encountered before. Y equals mx plus b, write your regular line graph. Knowing one variable, can I calculate the other one? Where it starts to get a little bit more complicated, though, is what if instead of 2 variables, I have 200 variables, right? And that's where the mathematics gets a little bit more complicated, which don't have time to go through everything, but at least I know this crowd well enough to know that having a couple of equations, goes a long way. So this first thing I want to, equation right here, look, this is it. This is y equals mx plus b. It just looks a little bit fancier than that. There's a couple of other things that I might as well touch on while I'm here, though. There's time series, there's random forest, there's multivariate adaptive regression splines, not to be confused with reticulating splines for anybody in the room who is a fan of SimCity, and ordinary least square models. So regression analysis, we already talked to a little bit. Time series varies a little bit, and I want to point this one out specifically because anybody who wants to go and take this and say, I'm going to use this in order to figure out what my shorts are going to be for the stock market tomorrow, it's a little bit more complicated, right? Because being able to figure out what X is in a given equation needs to have a little bit more added to it when you want to figure out not just what is it, but when is it, right? So this formula here goes a little bit more into the when calculation as well. So random forests. Random forests are actually another variation of something that you might have dealt with in computer science or whatever your background is, a decision tree, right? If this, then that, else this, right? What random forests do is they actually just take that and apply so many variations of it that instead of a tree, it looks like a forest, right? So that's kind of where they got the name on that. Multivariate adaptive regression splines, or MARS, really can be a little bit complex, but it's kind of an attempt to say, okay, well, if it's not a linear regression or it's not like a parabolic regression, what do I do when the data does not exactly line up the way that I want it to? That's when you use MARS. And then last, ordinary least squares. So one of the questions you might be asking yourself is, okay, well, I get it. I've got a lot of variables, but which ones do I actually use, right? If I've got that 200 set of variables, do I test each one, right? Generally, that is not the preferred approach. Generally, you use something like this equation to help you get in that direction. So in trying to come up with a compelling demo, one of the things that I wanted to do was to create something that applies to most, if not all of us. A predictive model for hard drive failures, right? Most of us kind of know a failed hard drive means data loss, it means angry customers, it means a lot of things that nobody wants, right? So wouldn't it be great if we could create a model that would allow us to predict when hard drives were going to fail? So, queuing that up to the next presentation, next demo.
Everything that we've been working on is using GCP, but GCP is not out there that has these types of tools. We just found that right now Google is leading in the market in terms of getting these things out to the public and making them easier to use. They're still kind of a force leader in that space.
Yeah, thank you. So in starting this journey, I did what any good data scientist would do. I tried to go to the internet to find out if this data had already existed somewhere. And as it turned out, yes. Yes, it did. So if you all are not familiar with Kaggle, Kaggle's a great place to go, but you can also just do Google searches anywhere to try to find good data sets in order to just come up with some models before you really get your hands dirty on things. It helps to just try some things out, right? So we're going to click on one that I've already created as well for the similar purposes of you are a lovely audience, but I'm sure you do not want to spend the couple of hours it might take for me to actually have this thing done. So what we end up doing, not dissimilar from the other model, is we just have to upload a CSV file. If you do use the Google tool BigQuery, of course, they're being accommodating and allowing you to upload from there as well. But just wanted to show, hey, all you have to do is put a CSV file in a cloud bucket, and you can immediately start getting some interesting things coming from that. So this is using a brand new tool. It was announced about 2 to 3 weeks ago. It's called AutoML Tables. It's their way of being able to do predictive analytics on structured data sets. So for anybody who's interested in taking a look at this later, highly recommended. I've had a lot of fun in the short time that I've already been working with this. So just in importing it, you get some good information, right? Column name, obviously, that's not too terribly hard because that's just what it's called, but it immediately looks at what variable type it is. So for example, it was able to predict that my date was a timestamp. It was able to figure out that, hey, a model type is a categorical set of data, right? Because you're only going to have so many of those model types. Another thing that they add in order to just make things easier for you is to be able to select whether or not there can be a non-answer associated with that, so that you don't actually get your model unduly influenced by lack of data integrity, which I appreciate that they're helping me out with that. So the first thing that you do is you kind of select what target column you want to work on, right? What are we predicting? So they kind of lock that out once you have that, and immediately some things start churning regarding what is the correlation between these values, and we'll get to that in a moment. But there's another couple of neat features here, right? Being able to do data splits. Again, my random number generator is probably not as good as Google's, right? My eeny, meeny, miny, mo for what's random. So I appreciate that they actually have some built-in services here to be able to say, okay, well, in this data set of 100%, we're going to take 10% out for validation, and we're going to take 10% for testing, and you don't have to go and do that, right? So right off the bat, it's easier than it would be with traditional data science, right? So column weight is another thing. Should I immediately say that one column is more valuable than another column, et cetera? In this case, I'm not going to select any of those because I kind of want to see, right, just out of the box, without doing any what data scientists love to say, hyperparameter tuning, which is just a fancy way of saying, okay, I'm going to adjust this and kind of see whether that influences the model. None of that, just kind of want to see what it does out of the box. And then if you do want to be able to flag time there, you can get something that's closer to one of those time series models that I was alluding to earlier, but again, not necessarily for what we're doing here. So depending on the size of the data set, it might take a little bit longer to jump from the schema column to the analyze column. We're using a slightly smaller data set, so it isn't necessary here. But it just goes to show that they've really done their homework in terms of building in some value even before you start training the model, right? Because you get some interesting things here, like some initial indications of what is the correlation with the predictive target. And we can see here that, hey, look, a capacity has a 12% correlation based off of some of the original analysis. So you get some interesting stuff here. So then training. So just move over to that next tab, right? Gotta love a GUI interface. And provided that it loads. What we'll see here is just a button that says train model, similar to the other demo we gave earlier, right? So already had a model trained. Again, we'll jump to that one versus waiting the couple hours it would take to get there. But just wanted to show you this interface here. Quotas, right? Who doesn't love quotas? But at the same time necessary to prevent the accountants from coming and hunting us down. So this is what allows us to do that. They provide a little bit of advice over what quotas make sense. And I kind of like this summary view because it actually allows me to double check right before I spend all of that money whether or not it's doing what I want it to do. And it's looking for a binary classification model, which makes sense because what we're looking for is this hard drive going to fail? It already split some things, and we kind of know how many columns and how many rows we have, right? So then let's move to the evaluate. So we get to figure out just how well this model building exercise actually went. Spoiler alert, maybe not the best. You get what you pay for in some cases.
Free cheap data set?
Yeah, free cheap data set, yeah. All right, so anybody with a data science background might be cringing a little bit when they see 100% accuracy and stuff, because if it's too good to be true, it definitely is in data science. So what this has done is it's created what's called an overfit model, which is one that is perfect for the data set that has been provided to it, but is probably not going to be able to generalize very well to anything that it sees after that. So this is kind of what we see here, kind of similar to the Tuesday keynote. They're talking about accuracy, precision, and recall. And then again, as we looked at earlier, while we would love to see this, a business user would love to see this, a data scientist would probably not, because having 100% accuracy there is a little bit troubling. This is actually my favorite part of the evaluation, because it actually does show me what weight was provided to all of those various variables that I tested it against. Again, you generally don't want to see that they have a 92% weight applied to a single column, especially when that column is date, right? But since we've already created the model, though, why don't we just take your first spin? Right, a predictive model is only as good as its ability to predict. So why don't we do that? Again, you can input it from BigQuery, or you could input it from a bucket. So let's input it from a bucket. I did isolate out a group to test with because I wanted to make sure that it was, again, data that the model had never seen before. So we're not going to select the same data set. We're going to take something that's derived from another one. All right. So then the other thing we've got to do is we've got to be able to put in to say, okay, well, where do you want this model to get its results? To put its results. So we do the same thing, right? We're just going to put it in an easy to find place, same place that we have our other one. So I'm going to send batch predictions just so you can see it, but then also, like some of the other examples we provided, I'm just going to go and show you personally what's happening there. What we have to do, though, is we have to actually open up the bucket that we put it in. So I'm going to go and do that. All right, here's my folder structure. And then we're just going to take one of these that was already created. And it's actually pretty nice that they have a tables and an error column here. So if something does go wrong, I can just click up this error CSV so that I can troubleshoot it. So that's at least one nice feature that they have here. The fact that the error CSV was small while the tables was large is a good start, right? It means that I did not somehow mess something up. At least when it comes to the data import process. So this is what we have here, right? Looks like a little bit of a mess, but this is what we're trying to predict here, the failure column. And if we jump to the end here, we have it's predictive for what was accurate and did it not fail or did it fail? Right? So the thing that's most important to us is being able to figure out, was it successful in predicting the failures? So let's do that. So here's 3 examples of a time where it failed. And oh no, it said with 93% confidence that it would not fail, which implies to me that we need to go back to the drawing board on this one. But as you could see, being able to figure out whether the data set itself is the problem in probably something like 10 minutes, plus whatever compute time you have, is a pretty powerful thing because data scientists are not cheap, as it turns out. Right. The other option is to just try to brute force it and give it enough time on that. But yeah, let's focus on a couple of other things here because we are running out of time. We're having too much fun. Right, so neural networks. Touched on a little bit earlier, but the way that I like to describe neural networks is you provide examples of what success looks like, and then the model itself determines what goes into it, right? Think about a system that's writing its own if-then statements, right? Dream come true. There's a reason why people like talking about neural networks. So this is more or less what it looks like. It's not dissimilar from the way that the brain works. Some might say that a neural network is a little bit of a misleading title because the way that synapses work in the human brain is different than hidden layers, but there are some similarities there too, right? What it comes down to is making a series of decisions based off of things that you've already been exposed to, and then once you reach either the correct result or the incorrect result, determining whether your internal decision-making process got you there, right? Seeing a nose means that this might be a face, But if it turns out that it's a nose on a dog, right, I might not associate that with a human face anymore once I kind of realize what that success criteria is. So one of the things I wanted to touch on in this talk is kind of talking about neural networks, and we do have a little bit of a tendency in the industry to just say, I can't figure it out, let's create a neural network to figure it out for us. And that isn't always the best answer for that, right? There's some reasons why neural networks are so popular now and making a resurgence versus when they were first created a couple of decades ago, as was discussed earlier. And having sufficiently large data sets are important, right? You probably shouldn't be using a neural network if you have less than 50,000 records. It's just one of those things where it's too susceptible to coming to the wrong conclusion for anything less than that. Again, predictive analytics, it's very helpful for being able to say, is this thing 1 or is this thing 2, and with how much confidence is that? There are other statistical or machine learning models that work for things that don't apply to predictive analytics. And then, yeah, sometimes it is just a matter of, okay, well, we've got all this data, we can't figure it out, we know there's a correlation, let's just throw it at a neural network and see what happens, right? And you do get some success with that, which is kind of where that comes from. So this was talked about in great detail on Tuesday. I love the keynote talk, right? Neural networks are applied for machine vision on autonomous vehicles. Love the work that's happening there, and it is a great application of that technology. So one of the things that we built as a part of what we're working on is a solution that we're calling Cornerstone, right? We want to address the aging infrastructure in the United States using technology. So we learned about some work that we were doing in Europe for inspecting wind turbines using autonomous drones. So we combined the need for addressing our aging infrastructure with this predictive maintenance with drones concept, and we came up with the architecture for what we're calling Cornerstone. And what we've done is we've taken Google Earth and Google Street View images, and we've run them through Google's Vision API for object detection in order to figure out what is it that's in these images, and then supplementing this baseline that's provided to us from Google with other models like the earlier pothole detection algorithm I showed you. So lastly, let's cover Cornerstone, which is the one that I'm most excited about because it's not just a model, it's a platform.
Right. We've been working on this platform for what, about better part of a year with the different use cases for this. As Ryan is booting this up, one of the use cases that I like the most is that I'm a Pennsylvanian, and fracking matters to me for various reasons, and we won't go down that path. But understanding fracking ponds, understanding if there are fences around the fracking pond, understanding if there's leakage that's going on, there aren't enough inspectors to go and do that work. So can we create a platform that allows me to help by flagging where you should look? So we have all of this information that's streaming in. How can I help you to say, you need to go to this quadrant, you need to go to this SR and check this out. There are a couple of other use cases along this line that we've been looking at for DEP in other states as well. But that was probably the one that meant the most to me when we were brainstorming on how we could really use this to provide when there are not enough people to do the work.
Thank you, Tracy. All right, so what we have here is your regular Google Maps interface right here. And we could put a couple of pins here just to provide some examples of some great spots that we found, because we can't exactly do quality control with the entirety of Google Earth. So we found this pretty interesting picture here, and let's dive right in, shall we? Quite literally, because this first one's underwater. This was a user-provided image, as you can imagine, because they don't have autonomous vehicles driving underwater yet, and I have questions if we ever get to that point. So we have this coral nursery here. Let's see whether the algorithm picks up these divers. So it was. It was able to predict that the image on the left is a person with 95% confidence, and that this person is a 66% confident. So we got a little bit ambitious on here, and so we kind of had function trump design in this particular case. We kind of wanted to see whether or not we could throw in some sentiment analysis using the available APIs as well. And we found that we could. We utilized the Facebook API in order to just do some sentiment analysis and look at Google Cloud Platform. What else? Probably should have done SATURN, but that was an afterthought there. And we were able to figure out not just what was identified in a particular post, but how people were feeling about it using the context of their conversation, right? So given that I only have a minute or two left, I wanted to be able to show that this has purely global scale. That was our intent. We're going to start with the widest application possible, and then we're going to narrow in as use cases identify themselves. Let's go to a place that I've never seen and figure it out. So with the exception of North Korea, we actually have just about every place mapped by now. So let's go to The Hague in the Netherlands. Anyone here from the Netherlands? No one? Okay. Well, worth a shot. We have quite the global community here. So if we could get rendering done better, you could see that there actually is a pretty good visualization just from Earth images these days. Yeah, so this will actually be able to help us in automatically identifying some problems. Right, well, this is not where I intended on ending up. As we build out the models, we should probably be looking for things that are user-provided images on the indoor. But let's go ahead and run it anyway, right? Let's see what happens if we can pick up some of these people here. And yes, we were able to predict that there were two people in this image. As we talked about earlier, you can notice that there's a third person in there that does not get picked up, right? So part of this becomes a matter of this is a starting point, and we built this platform in about less than 200 developer hours. So it goes to show you that there's plenty of opportunity for improvement, and that just right out of the box, there's already some power to some of these. So given that we don't have a whole lot of time left, go ahead and stop there and ask, does anyone have any questions?
Are there any AutoML tools that are not cloud-based?
Not cloud-based? So one of the things that we've actually been working on right now is being able to work on putting cloud models, like a train outside, bring inside type of model, to where we can put them on edge devices and put them on on-prem devices. Right now, they don't release the algorithm.
Right.
So that is a problem, is so that we would have to try to work around how to create something that was a black box that would work inside of an environment.
Yep. I'm doing a lot with fog
Yeah.
computing right now with the edge devices, and that's where I'm seeing it. So to Ryan's point, there's not the models themselves and how are not being, the algorithms behind the model creation are not being released yet, but they are giving and providing a way for you to at least port the model forward and have the model closer to the edge or closer to where you need it. And part of that is just the sheer compute that you need if you want to do it at speed, right?
Absolutely. Any other questions?
All right, so everybody's going home tonight, and you're all going to try and make a model. I'm not joking, guys. It's free, it's fun, and you can go out and Google the images that you want if you're into Marvel Comics. I'm serious. Do something fun.
Yeah.
All right, thanks everybody. Appreciate your time.